In this video, we're going to talk about the subspace topology. So here's our definition. Let X tau be a topological space and let A be a subset of X. Then the subspace topology for A determined by tau is tau prime, and it's the set of intersections of open sets U in the original space with the subset A. So tau prime is U intersect A for any U in tau or any open set in X. The members of tau prime are called relatively open sets of A, or in general just the open sets of the subspace A, and A tau prime is called a subspace of X tau. So let's quickly verify that A tau prime is a topological space. First, we have to show that the empty set and the entire set are in tau prime, and this is immediate. So the empty set and the whole set X are in the original topology tau, and that tells us that the empty set intersected with A, which is the empty set, is in tau prime, and that X intersected with A, which is X, is in tau prime. So good. Next, we need to consider arbitrary unions. So let's let VA be open in A comma tau. We want to show that, or A comma tau prime, we want to show that their arbitrary union is also open. So this tells us that V sub alpha is equal to A intersected with some U sub alpha open in X for all alpha, and therefore the union of the V alphas would then be equal to the union of these A's intersected with these U alphas, and that is A intersected with all the U alphas, the union of all the U alphas, and because tau is a topology, that means that the union of the U alphas is open in tau by definition of topology, and that tells us then that therefore A intersect the union of the U alphas is open, and so yes, these arbitrary unions of open sets are open in tau prime. Lastly, we want to show that arbitrary intersections of finite sets are open. So let's let V1, V2, Vn be open in A tau prime. So that tells us that Vi is equal to Ui intersected with the subset A for some Ui open in tau for each I. And so that tells us then that the intersection from I equals 1 to n of these VI's is equal to the intersection from I equals 1 to n of the Ui intersected with A. That's the intersection of these UI's, I equals 1 to n, intersected with A. This is open since each of the individual sets is open in X, and that tells us that this intersection I equal 1 to n of the UI intersected with the set A. It's an open set in X intersected with A that's in the subspace, and so yes, the finite intersection of elements of tau prime is in tau prime. So we've shown that the subspace topology is in fact a topological space. Let's look at an example. How about if we looked at the real numbers with the usual topology tau? That's where open intervals are open and any union and finite intersection of them is also open. Let's look at the subspace topology where we have Z, the set of integers, and we have the subspace topology tau prime given by tau as a subspace of the real numbers. So what are the open sets in this subspace topology? We're starting off with the real numbers, and we're only interested in like the integers of it as a subset and as a subspace, 0, -1, 1, etc. And so let's think about, what's an open set in here. So first of all, any open interval is an open set. So, for example, negative 1.5 to negative 0.5 is open in R with the usual topology, and that tells us that Z intersected with negative 1.5 to negative 0.5 which is equal to, okay, what's in there that's an integer? The only thing that's in there that's an integer is the integer negative 1. So the set containing just negative 1 is open in Z with the subspace topology here. So similarly, any singleton set is going to be open. So X is open in Z tau prime for all X in Z. What else is open? Well, any, if we took the union of, if we took any open set, negative 4.5 up to, or whatever that is, negative 4.5 up to 4 or something like that, then, this subset of integers is also open, negative 4, negative 3, ... up to, I guess 4 wasn't included, so up to 3. That would also be open in this subspace topology, the intersection of that open subset of R with the integers. And since any singleton set is open, that means that for any set B that is a subset of the integers, B is going to be equal to the union of all elements of B, the union of the singleton sets. So that tells us that that is going to be open, again, in Z tau prime. And so what sets are open in Z tau prime? All subsets of Z are open in this topology. So all subsets of Z are open in this topology. That tells us that, in fact, tau prime is actually the discrete topology in this case. The topology in which every subset is open. Let's think about what it means for a set to be closed in the subspace topology. So, in any topological space, D is closed if D complement is open. D complement's open if and only if D, which is equal to A minus D in the subspace topology, is open. That means that it's equal to U intersected with A, some open U in X, for some open set U in X. So that's what it would mean for D to be closed in the subspace topology, or relatively closed. So here's a theorem just stating that if A tau prime is a subspace of the topological space X tau, then equivalently a subset D of A is closed in A if and only if D is equal to A intersect C for some closed set in C. So you could either think about A intersected with a closed set C in X, or think about the complement of D being equal to U intersect some open set U intersected with A in X. So either way will work. This proof is pretty clear and it's in the book, so I'll just let you take a look at it. Here's an example. Let's look at the real numbers with the usual topology tau. And let's look at the interval, the closed interval, A equals the interval from 0 to 1, and give it the subspace topology tau prime. So let's look at each of the following subsets of A comma tau prime. Are they closed and are they open? So these are all intervals. So think about whether they are closed or open in the subspace topology in this case. Okay, so is the interval 0, 1 open? Yes, 0, 1 is open. Is it, and it's open because 0, 1 is open in the original topological space, and 0, 1 intersected with A is just itself. So yeah, it's open. Is it closed? Well, if it was closed, it would have to be equal to the intersection of some closed. So it would have to be the case that 0, 1 is equal to C intersected with 0, 1 for some C closed in R. Is that the case? No. Like if it's equal to the intersection of our subset A with some closed set, no, this would just be, C would have to be the open interval from 0 to 1, and that's not closed in R, in order for that intersection to work. Okay, so we figured out that this is open and not closed as we expected. What about the closed interval 0 to 1? Well, this is the entire set A, so this is both open and closed. We showed it was open above, but this is and it's also closed in this set because 0, 1 is equal to 0, 1 complement in this set is going to be equal to the empty set, which is open. So this set is both open and closed. It's the entire subspace. How about the typically half open interval from 0.1 to from 0.5 to 1? Now that is equal to say 0.5 to 1.5 intersected with A. Our set A is 0, 1. And this is open in the larger topological space. So it's a subset. So this set is equal to our subspace A intersected with a set that is open in R, and therefore this is open. Is it closed? No, this is not going to be closed. We could look at its complement. So its complement inside of A is 0, 0.5, and this is not going to be equal to A, which is 0, 1 intersected with U for any open set U in the real numbers with the usual topology. So this is open, but it is not closed in this subspace. And lastly, 0.5, 0.7 is closed. It is equal to, well, 0.5, 0.7 is closed in R in the usual real numbers, and therefore 0.5, 0.7 intersected with our set A is just itself, and so yes, it is closed in this closed in A with the subspace topology. It's not going to be open. It is not equal to the intersection of any open set in R with the set A. We can use the technique of a subspace topology to get kind of interesting mathematical spaces. So for example, the torus is a common mathematical space, and this is just like an inner tube. So one way we could get it as a subspace of R3 with the usual topology. Remember R3, that's a metric space, and it just is made up of balls of positive radius, so three-dimensional balls centered at points, and anything that's a union of elements like that or a finite intersection of elements like that is going to be open in R3 with the usual topology. So a torus, this is an inner tube that's hollow inside. We could think of it as a subspace of R3 with the usual topology, and we could take a circle of radius 1, for example, in R2. So this is that circle of radius 1, and center it at a point. And then we could just sweep it around. We could rotate it about the z-axis, and that would give us our torus, so this hollow inner tube, and that we can give the subspace topology, so we can think of that as a topological space. Okay, A property P of a topological space is called a hereditary property if it's the case that for any topological space x tau, if it has property P, then every subspace of x tau must also have property P. So first and second countability are both hereditary properties. The explanation of this is in the book. Separability is an example of something that is not hereditary. Just to give an example, this also happens to be in the book, but it's a sort of harder one to maybe draw or think about, so I'm going to go ahead and do it. Let's think about a new space x, and x is kind of a funny space. It's the real numbers together with the 0.01. So now this is a 0.01. So here we've got our 0.01, and our entire topological space is the real number line together with that point. So that's our original space set x, and our topology on x is going to be defined in this way. It's the empty set together with sets U subset of x such that the 0.01 is an element of U. So, for example, that tells us that the interval from 2 to 4, the interval from 2 to 4 interval is not open in x with this topology because the 0.01 up above is not in it. Whereas, for example, let's say -3 to -2, the closed interval from -3 to -2 union the 0.01 and unioning with a point, so I would want to take it as a set, is open in this topological space x tau, because the only criteria is that this point is in it or that the set is in fact the empty set. Okay. So this example is meant to show that separability is not hereditary. So to be separable means that the topological space has a countable dense subset, and this sort of weird space x comma tau was designed to have a specific dense subset. This dense subset is just the set containing the 0.01. So this is dense in x. Every open set in x that's not the empty set must contain this point, and so every open set intersects with the point, and therefore the closure of this the set containing just this point in this topological space is the entire set. Okay, now let's consider a subspace of this. Let's consider the subspace consisting of just the real number line, r comma tau. So this is a subspace of x tau. And so our question is, what are the open sets in this new subspace? So let's let B be just an arbitrary subset of the real numbers. Then B could be considered to be equal to B union this one point intersected with R. B is equal to whatever B was in the real numbers, some set, union together with this point, and then we intersect it with the real numbers again and effectively take it away. And by definition, any set that contains this point is open in x tau, and that tells us that, okay, B is equal to some open set in x tau intersected with the subset we're interested in, and that tells us that B is open in this subspace topology R comma tau prime for any set B subset of R. So that means that tau prime here is the discrete topology on the real numbers, and this has no countable dense subset. So we've shown that being separable is not a hereditary property, because we see that X tau is separable, has a countable dense subset, but its subspace, this particular subspace R tau prime, does not have a countable dense subset.